All right, thank you. So I'm going to be talking about turbulence in multi-phase gas in the CGM with crappy data. So the context is, sorry, the ISM with crappy data. The context is the CGM. So G is 0 in this talk. Okay, and so, you know, what I'm going to be talking about is stuff where there's typically 2 phases, something at 10 to the 6th, something at 10 to the 4 in pressure balance. So there's overdensities of about 100, sometimes 1,000. All right, so I don't think I'm going to get to this at all. I am just going to talk about something which is a little bit loony, but bear with me. It's the last talk of the day. So Zipf's law. Zipf was a linguist who noticed that you know, word length had a power law distribution, right, which was basically equal length of words per logarithmic interval. So you know, when I was a young and clueless postdoc, I ran around giving talks with this slide. And you know, like, I remember a senior faculty member took me aside and said, "Listen, kid, stop doing that. You're never going to get a job. You'll be homeless. Just like, don't do it." But then, to their eternal regret and my amazement, UCSB thought I was joking, and they gave me a job. So anyway, they've had many years to repent, you know, of the error of their ways. And so my goal today, I think it's too high a bar for a topic like this to say I'm right. I would like to be wrong in an entertaining and hopefully interesting way. Okay. So, you know, is there a characteristic scale for cold gas in a multi-phase medium? Here, cold is stuff that's photoionized, so stuff at 10 to the 4 K. So, you know, in previous years, you know, okay, why does this matter, right? So, basically, the size scale of the cold gas affects a bunch of things: covering fraction, whether clouds can survive, radiative transfer, you know, kinematics, and, you know, things that, you know, simulators really care about, which is like numerical convergence, right? So what do you need to resolve? And, you know, in cosmological simulations, you refine and you refine, and you just get more and more cold gas. So that's not great. And so, you know, we tried this, and there's a bunch of different length scales you could think about. You could think about a length scale where a parcel of gas can maintain sonic contact with its surroundings, right? So you know that MHD or hydro is scale free. So any scale has to be introduced by non-ideal processes. With radiative cooling, it's some sort of cooling length. Mike McCord came up with this idea of, you know, essentially a shattering scale. If you cool very rapidly, you lose sonic contact with your surroundings down until you hit the minimum of this quantity CST cool. But then Max Gronke asked the question, well, you know, is that stuff going to survive? And if you want to have it survive, it actually has to be somewhat larger than that, about an order of magnitude or more. So this is a problem, right? So the resolution is that, okay, this is a sort of pretentious way of saying that that it's probably scale free, right? You know, fractals are scale free. And if you take a turbulent box, right, and so this is simulations that the great Max Gronke ran. I should say this project was done in collaboration with Max, and the key theme for this was intermittency. Get confused, give up, and then try again. And so I think we're converging. So if you actually look at the mass function of cold gas, then it is more or less a power law with this slope of you know, m to the minus 2, which is equal mass per logarithmic interval. And the important thing about this is that you can have the large clouds that you need to grow, right? You need to survive by the criteria he found before, but the area is dominated by small scale stuff. You know, it's fog. You know, if you have clouds and you have fog, you're more likely to intersect fog, right? So, but there's a broad distribution of mass. So just to give you an idea of what we're talking about, you know, this is just a box. You know, you stir it, there's radiative cooling, and you know, you measure the mass function of cold gas. So where does this come from, right? this is something, and I should say this has been seen by other groups, you know, Drummond, Ransom Simulations, where you saw this, you know, way back in 2014, Yuan Li had some simulations with this, and of course, you know, yes, there's plenty of this in the ISM context. This has been seen many, many times. So this is something, it's not just a power law, but it's a special power law, right? It's a power law where if you write the mass per logarithmic interval, it's roughly constant. So where does this come from? It comes in a lot of contexts. Maybe these were not the best figures, it's something I found from Googling, but you know, cosmic rays, roughly, very roughly, you have equal energy per logarithmic interval. In dust, I know it's hard to see from this plot, but actually it obeys a similar scaling, right, with dust sizes, IMF to some extent, and it appears in many fields which outside physics, right? So the original field that Zips talked about, city sizes, if you take the population, right, and YouTube subscribers, income, you know, whatever, the S&P 500, what the capitalization, all kinds of stuff. And, you know, there's been a lot of literature on this, and a lot of ideas keep getting rediscovered. This was a very interesting paper where they, you know, they just listed how many times a certain idea had been discovered. And one of the examples was Fermi acceleration. They were like, oh, these physicists, they're not aware of this great work by Yule, and they reinvented the same process. So I would say that a lot of these ideas in this talk are actually not new, right? So I think the paper we were most influenced by was this one. He's an economist. This has, you know, thousands of citations, but trying to make it work was hard. And anyway, you'll see what happened. So why I somehow, for some reason, I love power laws, right? It's something where you actually have minimal information. You have one dimensionless number. And, you know, I guess the condensed matter physicist will tell you all kinds of profound things about universality and phase transitions. To me, I think the most interesting thing, or at least a motivation, is that power laws are often a sign of conserved quantities, right? And you also need scale invariance. So what in the old Soviet school we call intermediate asymptotics, right? You're far from boundaries, right? There's some range where you have scale invariant behavior. So you're familiar with things like, you know, Taylor setoff, where you get power law behavior, and you can just get it from dimensional analysis, right? Turbulence is a classic example, right? Kolmogorov, you have conserved energy flux, and you can just get the scalings by dimensional arguments. There's another class, fancy, and you get it by solving an eigenvalue problem, and it's invariant to renormalization group. I always fantasize that it would actually be this because it's cool, but it's not. I don't think so. So the natural thing to think when you're thinking about Zipf's law or some sort of power law distribution in mass is that we're at turbulence conference, right? Cascade, right? You think some conserved quantity, you conserve mass, and you have a fragmentation cascade. And you can just do dimensional analysis just like you do for turbulence. You say this is the mass flux through different masses, right? You cascade from large masses to small masses. And if this cascade time is scale-free, right, it just has some power law scaling, then just like what you do for turbulence, you can get something like Zipf's law if this cascade time does not depend strongly on the mass. Okay, and if you look at the literature, the answers that people get can very often be just derived from this. They often derive it by very complicated methods, you know, some Smolachowski coagulation equation, but they get things that are Zipf law-like, and you can reproduce their answer by just looking at their assumptions. For instance, in the ocean, there's bubbles in breaking waves, and the cascade time, if you assume it's it scales like the Kolmogorov eddy turnover time, you can get something like this, and they run experiments. This looks pretty good. Dust and asteroids, similar story. The cascade time is some sort of collisional time scale. Dust suspensions, and it depends on the collision rate. So great. So this sounds plausible, right? And it's been applied in a bunch of different systems, which at face value seem quite similar. And so what you expect from this is a conserved mass flux, right, through different masses. And that's what we see in the simulations with tracer particles. You do have a conserved mass flux, but the problem is that the mass flux is zero. There's equal mass flux in going to high masses and to low masses. So, so that's bad. So, all right, if you've been sleeping, you can wake up now for 2 slides, and then you can go back to sleep. This is the main idea, okay? So the main idea is, let's think about a random walk, a diffusion-dominated process, okay? If you just have free diffusion, if you have some dye, right, and you put it at a source, it's going to diffuse out and make a Gaussian whose variance broadens with time. Now, suppose you do it in a swimming pool, right? Then eventually, the dye will be uniform across the swimming pool, right? So nothing fancy there. Now let's consider a multiplicative random process, right? Something that these guys like to call geometric Brownian motion. We're familiar with this sort of thing from shocks in the ISM, right? You multiply a bunch of random numbers which are uncorrelated. That's a random walk in log, and you get a log normal. But now, suppose you have reflecting barriers, right? Then you will get something that is uniform, a uniform distribution again, but it's uniform in log x, right? Because the barriers are reflecting, there's no flux past them, so the net flux is 0. And something that's uniform in log x will give you Zipf's law. So this is a basic idea, right? The devil is in the details, showing that this actually happens in our simulations. So now, if you know a lot of details, you can go to sleep again. So what are the relevant physical processes? You basically want to write down a Fokker-Planck equation, or you can write down a Fokker-Planck equation for what's going on in mass. So you can think, all right, first of all, we have mass growth, right? And it's consistent with something that is growing geometrically, meaning that m dot is proportional to m, right? And so log m is scaling with time. Here's exponential growth. This is not what you would expect for something in a laminar velocity field, right? Normally, you know, m dot is something, you know, there's some density, there's some velocity, and then it's proportional to the area, which scales as mass to the 2/3. And so you expect power law growth. And so this is because of something that Lachlan talked about and Drummond originally introduced into this field, with this idea that the interface is fractal. And so the area doesn't have the usual Euclidean scalings with volume, right? So it's not quite, this really should scale as D really should be 1. It's more like 0.8, 0.9. But this is enough to give you close to exponential growth. And then another process is sort of Fokker-Planck equation. You have advection. You also have diffusion. And the most likely culprit you'd think is just fragmentation. Where fragmentation is something where the mass of the fragment is proportional to the original mass of the object. This is actually something that Kolmogorov originally wrote a paper about. And he said fragmentation should give you a log normal distribution. But what we actually see, so we latched onto this for a long time. But the thing is that if you look at the tracer particles, this is roughly symmetric distribution about the mean growth rate, which is slightly, you know, this ratio is slightly bigger than 1. And you can fit this with a double Gaussian. But there's often times when the growth is faster than normal. So we think this is basically seeded by turbulence, seeded by fluctuations in the area. And so we think this is the more important process. So these two things are essentially self-similar. right? It's something that you would expect in a geometric random walk, advection in log m, diffusion in log m. But actually something that turns out to be crucial, which we see in the sims, is something which breaks self-similarity. Something you would not expect to be important in building a power law. And that's coagulation. So things can slam into one another. There's some stuff, there's a very neat process by which cooling itself can induce coagulation. So, and we wrote a paper about this, but here's some stuff. There's nothing in this box except radiative cooling and two phases. And look, they're coagulating together. Anyway, I don't have time to go into that, but you can also see this in the tracer particles. That so this straight line and the sort of particles scattered around it, this is advection, this is diffusion about that, but then you see this large jumps in mass. That's a small mass particle coagulating onto a large mass particle. That is something which breaks self-similarity because you can coagulate onto any arbitrarily large mass particle. It turns out that this is really important. So one way of describing 5 minutes. One way of describing a power law is it's a logarithmic Boltzmann factor. I don't know whether I really want to do this. I think, okay, so you're familiar with this derivation of Fermi acceleration, right? And there's this fact that you basically get two exponentials and you need some fine tuning that the acceleration time and the escape time have to be roughly comparable to get your standard -2 power law. And the genius of Bell was to recognize that this is something that actually happens at shocks. So there's also this issue of fine tuning, right? If you get a power law from your process, how do you manage to get it to be this -2? I just want to say that, you know, you can, if you just have regular diffusion, you get a Gaussian. But if you have two ingredients, negative drift and a reflecting barrier, that Gaussian will turn into an exponential. And if this factor, z, is actually a logarithm, you will get a power law. And the easiest example of this, you know, you can solve the Fokker-Planck equation, but the easiest example of this is to think about our own Earth's atmosphere, right? If there's negative drift due to gravity, right? All the stuff is exhibiting Brownian motion. There's negative drift due to gravity, and there's a solid surface. And because of that, the Earth, if it's isothermal, the Earth's atmosphere has an exponential distribution. You can get this from solving hydrostatic equilibrium, or you can think of this as a Boltzmann factor, right? It's a ratio of energies. All right. Now, the ingredient that I mentioned that's very important is negative drift. In terms of the cartoon I showed, this is, you keep trying to hit your reflecting barrier. Okay, think about the swimming pool, you keep trying to hit the wall. And I showed you something that was growing in mass. So how do you get negative drift? This is the thing that confused us forever, right? And it turns out that, you know, you can use stochastic calculus to show that if your variance, if your diffusion is much stronger than advection, then you will get negative drift in log of a quantity, even if that quantity is growing exponentially. And the easiest way to see this is if you think, all right, suppose I have 50% gains, 50% losses. My first year, I go from $100 to $150. My second year, if I have 50% loss, I go from 150 to 75. So geometric growth is asymmetric, and you tend to drift towards small quantities. And this is Warren Buffett's golden rule: don't lose money. All right, I realize I'm just sort of, these technical details are things that drove us nuts. But I think maybe the thing that might convince you that there's something to this, you can just do Monte Carlos, right? You can just say, all right, I'm going to have something that has advection, it has diffusion, and suppose diffusion is a lot stronger than advection in log m. I'll have exponential growth. I'll have linear decline in log of the quantity, even though I have exponential growth, right? And so that shows that argument was fine. And to get a reflecting barrier, right? So where does this reflecting barrier come from? I had a swimming pool where I wanted to have diffusion, and I need to have the reflecting barrier so that I'll get a uniform distribution. And that comes from this coagulation that I mentioned, right? Something that breaks a self-similarity. And you can show that this is an additive process in log M. And you can show that it actually acts like a reflecting barrier. And these things are called Keston processes. And how much time do I have? You can actually run Monte Carlos of the same thing. So no reflecting barrier, you get a log normal. If you have a reflecting barrier, you get a power law. And you have, if you add numbers, basically what happens is that the small if you're small, then you just get repelled, right, from the origin. And it effectively acts like a reflecting barrier, and you get a power law again in your Monte Carlos. So, yeah, these are details you probably really don't care about. But I guess what I will say is that you don't need to have fine-tuning to get the -2 power law. You basically need something where diffusion is a lot stronger than coagulation, and you'll automatically get the -2, and you can also test that in Monte Carlo simulations. So that's probably a bit more detail than you care about, but I think the basic idea you can get behind. If you have a multiplicative process, you're going to diffuse in log M, and if you have some process, an additive process that repels you from the origin, that acts like a reflecting barrier, and then you end up with a uniform distribution in log M. Yeah.
Maybe not so much relevant to your talk though. So we know the stochastic acceleration is a random walk, not in E, not in energy, but in also log E, and they give you a power law spectrum. Any insight on that based on what you talk?
So that's something where you don't get -2 automatically, right? There's these two time scales, the acceleration time and the escape time, and unless they're comparable, you get power laws, but they vary depending on this ratio.
Mm-hmm.
So I think that it's not quite the same thing, because that's a system where you have escape from the system, right? This is something where
so
we're
if
conserving mass.
Right.
Yeah.
I mean, if you don't have escape, then you have -1.
If you don't have escape, yes. But the thing is, that system does not have this reflecting barrier that I talked about. So I think it's in a different class.
Okay. Sorry,
yeah.
I deviate a bit far from that.
Okay, if you thought that was deviating far, I mean, I think you opened yourself up, obviously, to this question of what is the origin of the power law distribution of words? What's the reflecting barrier in that case?
So I'm not gonna. Well, I guess a word can't be less than one letter. So in some sense, that's potentially the reflecting barrier. In other contexts, like the size of cities, economists, they talk about, well, there's some government funding steps in, all of that. I will have to say that, this is being recorded. There is not much contact between the theory and the data in those fields, as far as I can tell, but.
I thought that was an excellent talk, and I really loved your going into economics after we start in physics.
I think finally my parents might think that there's something to this.
Okay.
Actually, I guess on a more serious note, how do you define clouds in this multi-phase problem? And is it clear that that's actually the right statistical description of what you're seeing?
No, that's completely fair. So Clouds are what a cloud finding algorithm finds. That's our definition. I mean, it's a friends of friends or some segmentation algorithm. Yeah, not clear.
I think earlier we learned that in MHD simulations, the fractal nature is different. So would you predict different power laws?
So Max and
did you
his
see it,
student,
actually?
Hitesh Das,
MHD, right?
I think.
Yeah.
Yeah, so they did the same thing in MHD, and they have the same power law.
Oh.
It's surprising, I agree.
Okay, so how do you explain it?
We have yet, basically, at face level, that explanation is that the turbulent velocities and the turbulent driving they have is not very different. But we haven't analyzed those simulations with tracer particles and all that. So.
What I would say is that in those simulations, they run relatively low resolution simulations, and they're basically only resolving the outer energy containing scale of the turbulence, and that effectively acts as your dissipation, and that will match whatever level of turbulence you have there will be your dissipation. It doesn't mean that the changing of the fractal dimension is being correctly accounted for.
I mean, I think they drive it so that it matches the hydro simulation, the turbulent velocity at the outer scale matches. Yeah. So even though they're putting in more energy to do so.
Yeah. What I guess I would say, what I would say is that when you're driving turbulence like that, you're sort of putting in the in these sort of really hard to resolve problems, you're putting in the diffusivity by hand. So it's not necessarily surprising that they give the same result.
So the effect, the magnetic field doesn't have like a surprise, the fragmentation, or I don't know whether it applies to this.
Yeah, so it potentially does. I think in the end we've decided that mass diffusion is the more important thing is the variation in the growth rate rather than the fragmentation. And I would say that an important part of this, which I'm sure you don't care about, is that you have to solve this problem in co-moving coordinates. I actually didn't, but you can only see the negative drift if you have co-moving coordinates where you already take out the mass growth, and then you can see the negative drift. But yeah.
Okay. Yeah. So let's thank Peng again.